These are the answers to the AP Chemistry packet that is entitled Unit 8, Summative Assessment Practice. On this slide, you can see Unit 8 at a glance. Unit 8 is entitled Acids and Bases. In this video, I will present practice problems that cover all of the topics in Unit 8. This video should help you to prepare for the Unit 8 summative assessment. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Okay, let's get started. The instructions that you see on this slide are the same instructions that you will see on the AP Chemistry free response section. Show your work for each question in the space provided. Examples and equations may be included in your responses where appropriate. For calculations, clearly show the method used and the steps involved in arriving at your answers. You must show your work to receive credit for your answer. Pay attention to significant figures. Question 1 says the following. The value of Kw is affected by changes in temperature as shown in the table below. Part A. Use the information in the table above to calculate the pH of pure water at 20 degrees Celsius and at 30 degrees Celsius. Write the pH values in the table above. Now, if we begin by taking a look at the section of the AP Chemistry equations and constant sheet that deals with Kw, we can see that the definition of Kw is it's equal to the concentration of the hydronium ion, H3O+, times the concentration of the hydroxide ion, OH-, and that at a temperature of 25 degrees Celsius, the value of Kw is 1.0 times 10 to the negative 14. So from the information in this table, we can see that the value of Kw is affected by changes in temperature. So at 20 degrees Celsius, Kw is not 1.0 times 10 to the negative 14, but it's actually 6.8 times 10 to the negative 15. And we can also see at 30 degrees Celsius, Kw has a different value. It's 1.5 times 10 to the negative 14. So let's begin with 20 degrees Celsius. I'm going to write the Kw expression, and then we have to remember that in a sample of pure water, the concentration of the hydronium ion is always equal to the concentration of the hydroxide ion. So all we have to do now is take the square root of the Kw to determine the concentration of the hydronium ion. So in a sample of pure water, the concentration of the hydronium ion is going to equal the square root of this Kw value, which is 6.8 times 10 to the negative 15. So we take the square root of that number and we get 8.2 times 10 to the negative 8 moles per liter. So that value is the concentration of the hydronium ion in a sample of pure water at 20 degrees Celsius. Now, looking back on the equations and constant sheet, the pH is defined as the negative log of the concentration of the hydronium ion. So when we take the negative log of 8.2 times 10 to the negative 8 moles per liter, we get a value of 7.09. So 7.09 is the pH of a sample of pure water at a temperature of 20 degrees Celsius. Now, just a brief comment about how I rounded off my value for pH. So 8.2 times 10 to the negative 8 moles per liter, that value has two significant figures. But with respect to taking the negative log of that number, whether that's to determine the pH or the pOH, only the digits that are located to the right of the decimal point are considered to be significant when you do pH calculations. So that means that even though it looks like 7.09 has 3 digits, in fact, only the 0 and the 9 to the right of the decimal are considered significant digits. So 7.09 actually has 2 significant digits. All right, now let's follow the same procedure to determine the pH of a sample of pure water at 30 degrees Celsius. We'll start with the Kw. Again, in the Kw, that would be concentration of hydronium ion times concentration of hydroxide ion, and those are equal to each other in a sample of pure water. So I'll take the square root of 1.5 times 10 to the negative 14, and then that will give me the concentration of the hydronium ion in a sample of pure water at 30 degrees Celsius. Now I'll take the negative log of 1.2 times 10 to the negative 7 to get the pH. So the negative log of 1.2 times 10 to the negative 7 gives me a pH of 6.92. Now, even though the question in part A did not ask us to calculate the pOH value for pure water, if we had done that, it would be identical. So because in a sample of pure water, the concentration of hydronium is always equal to the concentration of hydroxide, that means in a sample of pure water, pH will always be equal to pOH, no matter what the temperature. pH always equals pOH in a sample of pure water. All right, well, hopefully those answers made sense. Let's go ahead and move on to part B of this question. And so in part B, it gives us the equation for the autoionization of water. And it says, is the forward reaction classified as endothermic or exothermic? Justify your answer by describing the relationship between temperature and kW. In one of my previous videos for Unit 7, Equilibrium, when I was talking about Le Chatelier's principle, I mentioned that when you change the temperature of the system, then the value of K will be affected. So take a look at these examples. If you happen to have an endothermic reaction and the temperature of the system is increased, then the equilibrium system will shift from reactants to products, from left to right, and this will cause the value of K to increase. But on the other hand, if you happen to have an exothermic reaction and you increase the temperature, then the equilibrium system will shift from the products to the reactants, or from right to left, and this will cause the value of K to decrease. Let's go ahead and take a look at the table and see how is kW affected as the temperature of the system increases. So when we change the temperature from 20 to 25 to 30 degrees Celsius, take a look at the value of kW. It will change from 6.8 times 10 to the negative 15 to a value of 1.5 times 10 to the negative 14. So we can see that the value of kW increases. So as the temperature increases, the value of the equilibrium constant, kW, also increases. So based on our understanding of Le Chatelier's principle and changes in temperature, that means that the forward reaction from left to right must be endothermic, since the value of K increased when the temperature increased. So the forward reaction for the autoionization of water must be classified as endothermic, because as the temperature increases, the value of kW also increases. All right, let's go ahead and take a look at part C of this question. It says, the pH of a sample of pure water that is at a temperature other than 25 degrees Celsius is determined to be 6.85. In each column of the table below, circle the correct information for this sample of pure water. So I'm going to begin by focusing on the right side of this column, which is entitled Relative Concentrations of the Hydronium Ion and the Hydroxide Ion. When you were studying topic 8.1, Introduction to Acids and Bases, you learned that pure water is called a neutral solution, and in pure water, the pH is always equal to the pOH, and that the concentration of the hydronium ion is always equal to the concentration of the hydroxide ion in a sample of pure water at any temperature. That's why we should circle that choice in that column on the right, that the concentration of the hydronium ion is equal to the concentration of the hydroxide ion in a sample of pure water at any temperature. Now, let's focus our attention on the temperature. We know that the pH of this particular sample of pure water in part C is 6.85, and we have to decide, is the temperature of this sample of pure water less than 25 degrees Celsius or greater than 25 degrees Celsius? Well, based on the trend in the table that we have determined so far, we can see that when we go from a temperature of 20 to 25 to 30 degrees Celsius, the temperature is increasing, and look what happens to the pH. The pH decreases as the temperature of pure water increases. So therefore, if the temperature of pure water is increasing and the pH goes from 7.09 to 7.00 to 6.92, then at 6.85 for the pH, we can assume that the temperature is even higher than 30 degrees Celsius. So we can select greater than 25 degrees Celsius for this particular sample of pure water in part C. Hopefully that makes sense. And now, before we move on to question 2 in this packet, I'll just remind you that for the remainder of this assessment, you can assume that the temperature is equal to 25 degrees Celsius. All right, let's go ahead and take a look at question 2. It says a student combines two different solutions that are labeled as A and B. Information about these two solutions is listed in the table above. So solution A, the volume is 350.0 milliliters, and it's a 0.016 molar solution of perchloric acid, HClO4, and solution B has a volume of 450.0 milliliters, and it is a 0.012 molar solution of potassium hydroxide. Part A, write the net ionic equation for the acid-base reaction that occurs when solutions A and B are combined. Now, there is a list of the 6 strong acids that AP Chemistry students should memorize for the AP Chemistry exam, and perchloric acid, or HClO4, is one of the 6 strong acids on that list. As far as strong bases are concerned, in general, strong bases are metal hydroxides, where the metal is an element located in either group 1 or group 2 on the periodic table. And since potassium is located in group 1, potassium hydroxide is classified as a strong base. Now that we know that HClO4 is a strong acid and KOH is a strong base, then we're going to split these substances up into separate ions as we're preparing to write this net ionic equation. So since HClO4 is a strong acid, we're going to write it as H plus and ClO4 minus because it is 100% ionized in aqueous solution, and potassium hydroxide, because it is a strong base, we will write it as K plus and OH minus because it completely dissociates into separate ions in aqueous solution. Now the H plus and the OH minus, they come together to make water. So water is one of the products, and then the other product is an ionic compound, and that would be potassium perchlorate, which is KClO4. And since potassium is one of those 4 soluble SNAP ions, another thing to memorize for the AP Chemistry exam, the SNAP ions are sodium, nitrate, ammonium, and potassium. That makes potassium perchlorate a soluble ionic compound. So we're going to split that up into K plus and ClO4 minus. Now, hopefully, you can see that on the left side of the equation and on the right side of the equation, we have some spectator ions. Let's cross off the potassium on the left and on the right, and let's cross off the perchlorate on the left and on the right. Once we do that, now we have our net ionic equation. So when you have a strong acid reacting with a strong base, the net ionic equation will be H plus OH minus to produce water. And you may already know that H plus and hydronium can be used interchangeably. So hydronium is H3O plus, and if you change that to H3O plus on the left, then you would need 2 moles of water on the right to balance the total number of atoms. So either H plus OH minus to make water could be a possible correct answer to number 2, part A, or you could say H3O plus OH minus to produce 2 moles of water. Now let's go ahead and take a look at part B of this question. In part B, we have to simply calculate the pH of solution A. So solution A is 0.016 molar HClO4, which is perchloric acid. And perchloric acid is one of the strong acids that you should memorize for the AP chemistry exam. So this question falls under topic 8.2, pH and pOH of strong acids and bases. Molecules of a strong acid, and again, here you can see the list of 6 strong acids, and HClO4 is on that list, will completely ionize in aqueous solution to produce hydronium ions and the conjugate base of the acid. So the concentration of the hydronium ion in a strong acid solution is equal to the initial concentration of the strong acid. So that means that not only is 0.016 molar the concentration of the perchloric acid, that is also the concentration of the hydronium ion in solution A. So how do we figure out the pH of solution A? Simply take the negative log of 0.016 molar, which is the concentration of the hydronium ion in this strong acid. And when we do that math, we get that the pH of solution A is equal to 1.80. Now let's move on to part C of this question. Part C says to calculate the pH of solution B. Well, solution B is not a strong acid, but solution B is a strong base. We have 0.012 molar potassium hydroxide. And potassium on the periodic table is located in group 1. So this is an example of a group 1 hydroxide. So back to topic 8.2. When dissolved in solution, strong bases, for example, group 1 and group 2 hydroxides, completely dissociate to produce hydroxide ions. The concentration of the hydroxide ion in a strong base solution is equal to the initial concentration of a group 1 hydroxide. Now, if this were group 2, such as magnesium, calcium, strontium, barium hydroxide, then we would have to multiply by 2 to convert from the concentration of the group 2 hydroxide to the concentration of hydroxide. But this is a group 1 hydroxide. So KOH, we don't have to do anything extra. So 0.012 molar is not only the concentration of the KOH, or the potassium hydroxide, that is also the concentration of the hydroxide ion. If we take the negative log of 0.012, then we get on our calculator 1.92. But 1.92 is not the final answer to part C. All we have so far is we've calculated the pOH by taking the negative log of the hydroxide concentration. So remember, on the equation sheet you can see that the pKw, or the negative log of Kw, is 14. And 14 is the sum of pH plus pOH. So we just calculated the pOH. That means that all we have to do is 14 minus that value. So 14 minus 1.92 will give us 12.08. That is the correct answer to part C of question 2, that the pH of solution B is equal to 12.08. All right, let's move on to part D of this question. In part D, it says the final volume of the combined solution when solutions A and B were mixed together is equal to 800.0 milliliters. Assume that the acid-base reaction that occurred in this experiment has gone to completion. Identify the excess reactant in this experiment and calculate the number of moles of the excess reactant that remains left over at the end of the experiment. So if you're given a volume and a molarity, you can calculate the number of moles of a substance. So 350 milliliters, let's divide by 1,000 to go from milliliters to liters. So times 1 liter over 1,000 milliliters. And then 0.016, that's the number of moles per liter for the strong acid, perchloric acid. If we do this math of 350 divided by 1,000 and then times 0.016, this will not only give us the number of moles of perchloric acid, because perchloric acid is a strong acid, it's actually the number of moles of H+, or hydronium ions, in solution. And so we get 0.0056 moles of H+. Let's do a similar calculation for the potassium hydroxide to figure out the number of moles of hydroxide ions. So it'll be volume times molarity, but that should be volume in liters. So 450.0 milliliters. Let's convert to liters. So times 1 liter over 1,000 milliliters. Let's multiply by the molarity, 0.012 moles of potassium hydroxide per liter. But that is also the number of moles of hydroxide ions per liter. So 450 divided by 1,000 times 0.012 gives us the number of moles of hydroxide ions. So that's 0.0054. Now these numbers are very similar to each other, but one of them is slightly larger than the other. So that's going to be our excess reactant, because H plus and OH minus react in a 1-to-1 mole ratio. We have a slightly larger number for moles of H plus. That's going to be our excess reactant. So the difference between 0.0056 and 0.0054, that difference will be how many moles of H plus remain left over at the end of the experiment. So H plus reacts with OH minus to produce water in a 1-to-1 mole ratio. We have 0.0056 moles of H plus reacting with 0.0054 moles of OH minus. So the difference between these two numbers represents the number of moles of H plus, the excess reactant, that remains left over at the end of the experiment. Now, 0.0002 moles is the difference, or you could write that in scientific notation. That would be 2 times 10 to the negative 4. That's the number of moles of H plus that remains left over. Now, to get the pH of the solution, we have to consider the total volume. So the final volume of the combined solution is 350 plus 450, or 800 milliliters, or that would be 0.8000 liters. So number of moles of leftover or excess H plus, 2 times 10 to the negative 4. Total volume of the solution in liters is 0.8. So moles divided by liters gives us molarity. And this will be the concentration of H plus. And it works out to be 2.5 times 10 to the negative 4 moles per liter. All we have to do now to get the pH is take the negative log of the concentration of H plus. So the negative log of 2.5 times 10 to the negative 4 moles per liter gives us our pH, which is 3.60. Now, that's the end of question 2. Let's move on to question 3. In question 3, it says, information about a solution of a monoprotic acid, HX, is listed in the table above. So we see the formula of the acid is HX. The initial concentration of the acid is 0.050 moles per liter. We don't know the concentration of the hydronium ion at equilibrium, but we do know that the pH of the solution is 3.07. Part A, calculate the value of the concentration of the hydronium ion in a solution of 0.050 molar HX. So if you're wondering how to start this problem, we're not going to use 0.050 to get the concentration of the hydronium ion. Instead, we're going to use a pH of 3.07 to determine the concentration of the hydronium ion. And that's because the definition of pH is the negative log of H plus, or the negative log of the hydronium ion. So therefore, the opposite of negative log is 10 to the minus something. So 10 to the minus pH, or in this case, 10 to the minus 3.07, gives us the concentration of the hydronium ion. So when we do 10 to the minus 3.07, we get 8.5 times 10 to the negative 4 moles per liter. Now, considering that the initial concentration of the acid is 0.050 moles per liter, but the concentration of the hydronium ion that we just got in part A is a much smaller number, this means that this is a weak acid, which is only partially ionized in aqueous solution. Now, in part B, they want us to figure out the percent ionization of this acid. in a solution of 0.050 molar HX. So if you forgot the definition of percent ionization, I will show you. I had presented this in an earlier video on weak acids. And so here you can see on this slide that the definition of percent ionization of an acid is the ratio concentration of hydronium, or H+, in equilibrium, divided by the initial concentration of the acid, and then times 100. So we're going to take 8.5 times 10 to the negative 4, which is our concentration of hydronium ion in equilibrium, divide that by the initial concentration of the acid, which is 0.050, and then times 100. And when we do that math, we discover that yes, this is a weak acid. It's only about 1.7% ionized in aqueous solution. Now, let's move on to question 4. It says, benzoic acid, which has the formula C6H5CO2H, ionizes according to the equation above. Part A, write the expression for the equilibrium constant Ka for the reaction. So normally for an equilibrium constant, it would be products over reactants, but remember that we do not include solids and pure liquids like water in the equilibrium constant expression. So it's going to be the concentration of the hydronium ion times the concentration of the benzoate ion, which is C6H5CO2-, that's the conjugate base of benzoic acid, and then divided by the concentration of benzoic acid. So that is our Ka expression for part A. Now in part B, it says to calculate the pH of a solution of 2.5 times 10 to the negative 3 molar benzoic acid. So what we're going to do to calculate the pH of this solution is use the equilibrium constant expression that we wrote in part A. We're also going to use the value of Ka, which we were given as 6.3 times 10 to the negative 5. We're going to do a calculation to determine the concentration of the hydronium ion in solution. And then once we get that value, we'll take the negative log of that number to get the pH. So in an earlier video, I had presented how you would solve for the concentration of hydronium in a weak acid. So on these next two slides, I'll show you a sample calculation. Then we'll jump back into the benzoic acid example. So on this slide, this was from an earlier video, and we had a different acid. This is propanoic acid, and the concentration of the propanoic acid was 0.50 molar. So you can see that I set up a rice table, and at the end of the rice table, I had the concentration of the hydronium ion as well as the conjugate base as X, and that was on the top of my Ka expression. And on the bottom of my Ka expression was 0.50 minus X. And then as you recall from that earlier video, I talked about how we can make the simplifying assumption for a weak acid that the value of X is much smaller than the original concentration of the acid, the weak acid. So then you can change the 0.5 minus X on the bottom to just the number 0.5, and that really does simplify the math. And then once you do solve for X, as I'll show you on the next slide, so once I solve for X, that number is the concentration of the hydronium ion in solution, and then all we have to do is take the negative log of that number to get the pH. Now let's dive back into the benzoic acid example. So here is our Ka expression from part A. And again, that is equal to 6.3 times 10 to the negative 5 because we were given the Ka in this problem. So I'm not going to make a rice table, but I'll just go ahead and cut to the chase, which is we now have on the top X, and on the bottom it would be the concentration of the weak acid, so 2.5 times 10 to the negative 3 minus X. We'll make that simplifying assumption to make the math easier because X will be smaller than the original concentration of the acid. So now I have X squared on the top, and I have 2.5 times 10 to the negative 5 on the bottom. All I have to do now is a little bit of algebra to solve for X. So X squared is equal to the product of 2.5 times 10 to the negative 3 and 6.3 times 10 to the negative 5 multiplied together. So X squared is equal to 1.6 times 10 to the negative 7 I will now take the square root of that number, and when I do that math, I get not my final answer, but I'm getting closer to the pH. I get 4.0 times 10 to the negative 4 moles per liter. That is my concentration of the hydronium ion in this solution. So I will take the negative log of that number, and when I do that math, the negative log of 4.0 times 10 to the negative 4 gives me my pH. So the pH of a solution of 2.5 times 10 to the negative 3 molar benzoic acid works out to be 3.40. Well, hopefully all those calculations made sense, and now let's move on to part C of this question. So it says that a student performs a titration experiment in order to determine the concentration of the benzoate ion, which has the formula C6H5CO2-, in a solution of potassium benzoate, which has the formula KC6H5CO2. So part C says write the net ionic equation for the acid-base reaction that occurs when solutions of potassium benzoate, so KC6H5CO2, and nitric acid, HNO3, are combined in this titration experiment. So we're actually switching from talking about benzoic acid. As you had seen earlier in part A of this question, it was about the behavior of benzoic acid. Now we're talking about a reaction between the weak base, the benzoate ion, and a strong acid, nitric acid. So what I'm going to do is start with writing the net ionic equation for the acid-base reaction that occurs in this titration experiment. Potassium benzoate is a soluble ionic compound, and we know this because potassium, K+, is one of those soluble snap ions that you learned earlier. So potassium and any negative ion should be a soluble compound. So what I'm going to do is split up the formula of potassium benzoate into K+, and then the benzoate ion is C6H5CO2-. So don't forget to include the charges on your ions. Now, since nitric acid, HNO3, is on your list of the 6 strong acids, then we are going to split that up as well into H+ and NO3-. So there's H+ and NO3-. So now you can see for the reactants, we have the weak base, the benzoate ion, reacting with H+ from the strong acid. So when those ions come together, they will form benzoic acid, which is classified as a weak acid, so we're not going to split up benzoic acid. That's going to be the product on the right side of the equation, but I'm going to write that as one formula, not split up into separate ions because it's a weak acid. And then hopefully you can see that the other product is simply the ionic compound, potassium nitrate. So potassium nitrate, KNO3, would be separated into soluble ions. So potassium and nitrate are going to be those soluble snap ions. And so now, like we have seen earlier, when you write a net ionic equation, you talk about the reactants and the products, but then you have to cross off any spectator ions that you see on both sides of the equation. So I'm going to go ahead and do that now. I'm going to cross off the K+ and the NO3- as spectator ions because they appear identically on both the left and the right of the equation. And so now we have our net ionic equation. The weak base, the benzoate ion, reacted with H+ from the strong acid to produce benzoic acid. So there is our net ionic equation, and you may remember that the hydronium ion, or H3O+, is a substitute for H+. So if you would prefer to write the hydronium ion, then you would have to also show water as an additional product on the right side of the equation. So either benzoate plus H+ to produce benzoic acid like this, or you could write benzoate plus the hydronium ion to produce benzoic acid and water. Now, before we look at part D of this question, let's examine the details regarding this titration experiment. So here's what we know so far. The student titrated a 50.0 milliliter sample of potassium benzoate. So we know the volume of the potassium benzoate solution, but we don't, at least not yet, know the concentration of the potassium benzoate solution. And so this solution was titrated with 0.90 molar nitric acid. The titration curve from the experiment is shown at right. And the two data points that are marked on the titration curve represent the following pH values. The initial pH of the potassium benzoate solution, which looks like, estimating from the curve, it was approximately 8.8 or 8.9 at the very beginning before the titration experiment started. And then we also know that the pH of the reaction mixture at the equivalence point in the titration looks like that is approximately 2.5. If you look along the x-axis, we can see that the equivalence point was reached at a volume of 20 milliliters. So we know from the titration curve that 20 milliliters of the titrant, 0.90 molar nitric acid, is required to reach the equivalence point. So when you are given both the volume and the molarity of a substance, you can always calculate the moles. So even before we take a look at part D of this question, we are already prepared from the information in the titration curve to calculate the number of moles of nitric acid that was required to reach the equivalence point in this titration experiment. So volume of the titrant is 20 milliliters. You would normally convert from milliliters to liters when you are doing molarity calculations. So 20 milliliters divided by 1,000 to go from milliliters to liters. And then if we multiply by 0.90 moles of nitric acid per liter, this calculation, 20 divided by 1,000 times 0.90, this gives us the number of moles of nitric acid that was required to reach the equivalence point in this titration. So this information will help us answer part D. Let's take a look at part D. So part D says calculate the concentration of the benzoate ion, C6H5CO2- in the solution that was titrated in this experiment. So in part C, we wrote a net ionic equation for the reaction that is occurring. And as you can see from this equation that was written in part C, there's a 1-to-1 mole ratio between benzoate and the strong acid, the nitric acid, which we represent as H+ in this net ionic equation. So therefore, the number of moles of nitric acid that reacted is the same as the number of moles of benzoate that was in the solution that was titrated. So the solution that was titrated contains 0.018 moles of benzoate. Now, of course, that's not concentration, but that is part of our calculation. So concentration would be moles per liter. And it said the student used a 50.0 milliliter sample of this potassium benzoate solution in this titration experiment. So moles of benzoate, 0.018 moles. Volume of the potassium benzoate solution is 50 milliliters, or 0.05 liters if we convert to liters by dividing by 1,000. And so now 0.018 divided by 0.05, that will give us the concentration of the benzoate ion in the solution that was titrated in this experiment. And so when you do that math, 0.018 divided by 0.05, we get 0.36 moles per liter. So that is the concentration of the benzoate ion. Now, you may recall in an earlier video when I was talking about how you would do titration calculations, there is another technique that will give you the same answer. Let me go ahead and show you that. So you can take, if you have a 1-to-1 mole ratio between the acid and the base, you can take this approach and you should get the same answer. So when there is a 1-to-1 mole ratio between the acid and the base, as we have in this example, then the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Again, this only works when you have a 1-to-1 mole ratio between your acid and your base. So the molarity of the acid we already know is 0.90. The volume of the acid that was required to reach the equivalence point was 20 milliliters as determined from the titration curve. The molarity of the base, or the benzoate ion, we don't know, so we're trying to find that value. And the volume that was given in this problem of the sample of potassium benzoate, that's the volume of the base, that was 50 milliliters. So 0.9 times 20 divided by 50 should give us the concentration of the benzoate ion, or the concentration of the base that was titrated in this experiment. So we did get that same value, which is 0.36 moles per liter. So you have two different ways of obtaining the correct answer to part D. Now, let's take a look at part E of this question. It says, when the pH of the reaction mixture in the titration experiment is equal to 4.80, do you predict that the benzoate ion, which is C6H5CO2-, or benzoic acid, which is C6H5CO2H, which one of these substances, benzoate or benzoic acid, should have a higher concentration in the flask? Justify your answer. So we know from the titration curve that the equivalence point in this titration was reached after 20 milliliters of the titrant was added. So half of 20 is 10. That means that the half equivalence point was reached after 10 milliliters of the titrant was added. Something special happens at the half equivalence point. So at the half equivalence point, that is, after 10 milliliters of the titrant is added, there are equal amounts of the benzoate ion and benzoic acid. So we know we have equal amounts of benzoate and benzoic acid at a point where 10 milliliters of the titrant is added. So on this titration curve, anything before the half equivalence point would indicate that there should be more benzoate than benzoic acid. In other words, the concentration of benzoate should be greater than benzoic acid before the half equivalence point. And then after the half equivalence point, the concentration of benzoate should be less than the concentration of benzoic acid. So now what we have to do is say, where would a pH of 4.8 fall on this titration curve? Is it going to fall before or after the half equivalence point? So hopefully you can see that if I look at a pH of 4.8, which is right here on the titration curve, that occurs before the half equivalence point. So one way you can answer part E is as follows. When the pH of the reaction mixture is equal to 4.8, this occurs before the half equivalence point in the titration. And so therefore the benzoate ion should have a higher concentration than benzoic acid. Now, before we take a look at part F of this question, let me give you an alternative way that you could have answered part E with a different justification. And this justification that I'm going to present, this falls under topic 8.5 and topic 8.7. So here, in topic 8.5, which is entitled Acid-Base Titrations, you can see I'm highlighting one of the essential knowledge statements, which says, for titrations of weak acids and bases, it is useful to consider the point halfway to the equivalence point, that is, the half equivalence point. At this point, there are equal concentrations of each species in the conjugate acid-base pair. For example, for a weak acid, the concentration of HA is equal to the concentration of A-. So that would be, for example, benzoic acid and the benzoate ion. They would have the same concentration at the half equivalence point. And then what's also relevant is topic 8.7, and I'm highlighting this portion of the essential knowledge statement, which says that when the solution pH is less than the pKa of a weak acid, then the acid form would have a higher concentration. On the other hand, when the pH of the solution is greater than the pKa of the weak acid, then the base form has a higher concentration. So for benzoic acid, if pH is less than pKa, then benzoic acid would have a higher concentration. On the other hand, if pH is greater than pKa, then the benzoate ion would have a higher concentration. So now back to part E. At the half equivalence point, pH equals pKa. And looking at the y-axis, you can see that's around 4.2 would be the pH at the half equivalence point. So pH equals pKa. At the half equivalence point, that would be around 4.2. Now let's compare 4.8 with 4.2. Well, you can see that if the pH of the reaction mixture is 4.8, 4.8 is greater than 4.2. And under the conditions that we've learned here, if pH is greater than pKa, then the concentration of A minus, or the conjugate base, in this case the benzoate ion, is greater than HA, or the concentration of the weak acid, benzoic acid. So another way you could have answered part E is the following. At the half equivalence point, pH equals pKa, which is approximately 4.2, and now we're talking about a pH of 4.8. pH of 4.8 is greater than the pKa, and therefore the benzoate ion should have a higher concentration than benzoic acid. So again, just another way of justifying your answer to part E. Now let's go ahead and take a look at part F. In part F, it says, a student makes the claim that bromophenol blue, an acid-base indicator with a pKa value of 4.0, would be an appropriate indicator that could be used to determine the endpoint for this titration. Do you agree or disagree with the student's claim? Justify your answer. So once again, let's take a look at topic 8.7, pH and pKa, but now I'm highlighting a different essential knowledge statement. To ensure accurate results in a titration experiment, acid-base indicators should be selected that have a pKa value that is close to the pH of the solution at the equivalence point. And now on this next slide, this is not from this particular packet, but this slide comes from my earlier video that included topic 8.7. And you can see what's highlighted in yellow in that box in the upper right corner of the slide is what I just mentioned, that when selecting an acid-base indicator for a titration, it's important to choose an indicator that will change color at or very near the equivalence point. So the best indicator to choose is one with a pKa value that is close to the pH of the solution at the equivalence point. So for this question, which is a different question, thymol blue was the best choice for determining the endpoint of the titration because the pKa of thymol blue, 2.0, is close to the pH of the solution at the equivalence point, which is around 2.5. All right, now back to part F. So a student makes the claim that bromophenol blue, which has a pKa of 4.0, would be appropriate. And hopefully you can see that that is incorrect, or we should disagree with the student's claim. Because bromophenol blue with a pKa value of 4 would change color at around pH of 4. That is not close to the pH of the solution at the equivalence point. It should be around 2.5. So the answer to part F is the following. I disagree with the student's claim. The pH at the equivalence point in this titration is between 2 and 3. And if bromophenol blue indicator is used, then the color change would occur at around a pH of 4, which is not close to the pH at the equivalence point. So another acid-base indicator should be chosen that has a pKa value close to 2.5. Now let's take a look at question 5. In question 5, we are given a table with information about two different acids. We have chloroacetic acid, which has the chemical formula Cl, CH2, CO2H, and then we have trichloroacetic acid, which has the formula CCl3, CO2H. We are also given the pKa value for each acid. So for chloroacetic acid, its pKa is 2.86. And for trichloroacetic acid, its pKa value is 0.66. We're also given the name and the formula for the conjugate base for each acid. So for chloroacetic acid, its conjugate base is called chloroacetate, and it has the formula Cl, CH2, CO2-. And for trichloroacetic acid, its conjugate base is called trichloroacetate. which has the formula CCl3CO2-. Now, in question 5, it says information about chloroacetic acid and trichloroacetic acid is shown in the table above. Part A, which substance, chloroacetic acid or trichloroacetic acid, is classified as the stronger acid? Justify your answer by comparing the pKa values of each substance. So we have a pKa of 2.86 and we have a pKa of 0.66. Now you know that when you take the negative log of the Ka value, you get what we call the pKa. So the opposite of the negative log is 10 to the minus something. So the Ka value is equal to 10 to the minus pKa. So on your calculator, if you do 10 to the minus 2.86, this is what you get. You get 0.0014. So that is the Ka for chloroacetic acid. And then you do the same process to figure out the Ka for trichloroacetic acid. 10 to the minus 0.66, that will give you a value of 0.22. That is the Ka for trichloroacetic acid. So what you should know as a summary of this information is that in general, the smaller the pKa value is, the larger the Ka value is. So trichloroacetic acid has a larger Ka than chloroacetic acid. And the larger the Ka value is, the stronger the acid is. So a larger Ka would indicate that the equilibrium system more strongly favors the products, indicating that the acid would ionize in aqueous solution to a greater extent. So a larger Ka is associated with a stronger acid. So the answer to part A is the following. Trichloroacetic acid is classified as the stronger acid because it has a smaller pKa value and therefore a larger Ka value. Now, before we take a look at part B of question 5, I'd like to talk about a comparison between Ka and Kb, which you can see as one of the equations on the AP Chemistry equations and constant sheet. So what do we know so far about the comparison of these two acids, chloroacetic acid on the left and trichloroacetic acid on the right? Well, we have determined that trichloroacetic acid is the stronger acid in that pair. Now, can we make a similar comparison to relate the relative strength of the base, chloroacetate, as well as trichloroacetate? Could we compare these two substances and decide which substance is the stronger or the weaker base? And the answer is yes, we can make that comparison. I'm highlighting the equation that says Kw, which is 1.0 times 10 to the negative 14. That is equal to the product of the acid dissociation constant, Ka, and the base dissociation constant, Kb. So there's an inverse relationship between the values of Ka and Kb for a conjugate acid-base pair. The larger the value of Ka, the smaller the value of Kb. So if one substance is a stronger acid that has a larger value of Ka, then its conjugate base will actually be weaker because of that inverse relationship between Ka and Kb. So a stronger acid should have a weaker conjugate base because of this inverse relationship between Ka and Kb for a conjugate acid-base pair. So without doing any math, but just by knowing that trichloroacetic acid is the stronger acid in that pair, then we can say that the trichloroacetate ion would be the weaker base. And so we're going to be set up for part B, and we'll take a look at part B. I just wanted to give you this relationship between Ka and Kb. So let's go ahead and take a look at the details of part B. It says which ion, chloroacetate or trichloroacetate, is classified as the weaker base. Unfortunately, we cannot use a Ka and Kb argument because it says justify your answer by using principles of chemical bonding to explain the difference in the relative stability of the two ions. So we cannot simply say the stronger the acid, the weaker the base. We have to look at specific features of chemical bonding. And so you can see in this table, there's a side-by-side comparison of the Lewis diagram for chloroacetate on the left and trichloroacetate on the right. So the difference is going to be associated with the number of chlorine atoms in that structure. Now on this next slide, this is from another question that I had presented in an earlier video where we were comparing the relative strength of 3 different acids, and those acids are HOCl, HOBr, and HOI. And it was determined that HOCl was the strongest acid in this set, and I had talked about electronegativity and the negative charge on the oxygen atom. So I'm highlighting this explanation on this slide. This is from an earlier video. As the electronegativity of atom X increases, this helps to stabilize the conjugate base. So atom X was either chlorine, bromine, or iodine. And because chlorine was the most electronegative, it helped to pull electron density away from the oxygen atom that carries the negative charge, and it helped to stabilize the conjugate base. Now let's go back to this question. Again, this is part B of question 5. We're comparing chloroacetate on the left with trichloroacetate on the right. So the question says, which ion, chloroacetate or trichloroacetate, is classified as the weaker base? Again, justify your answer by using principles of chemical bonding. So there is one chlorine atom that can withdraw electron density away from the oxygen atom that carries the negative charge in that ion, but then since trichloroacetate has 3 chlorine atoms, it can do a better job of pulling or withdrawing electron density away from that oxygen atom that carries the negative charge. So that's going to be the explanation involving the chlorine atoms and their electronegativity. So here's what I said. The trichloroacetate ion is the weaker base. Compared to chloroacetate, there are more chlorine atoms in the trichloroacetate ion. Chlorine is an electronegative atom, and the presence of additional chlorine atoms in trichloroacetate results in a greater pull on the electron density toward the chlorine atoms. Pulling electron density away from the oxygen atom that carries the negative charge will stabilize the conjugate base. And since trichloroacetate is the more stable conjugate base, it is classified as the weaker base. So it's using principles of chemical bonding, the fact that 3 chlorine atoms do a better job than just 1 chlorine atom of pulling electron density away from the oxygen atom that carries the negative charge, that helps to stabilize trichloroacetate, making it a weaker base. Now let's take a look at question 6. Question 6 says, a student titrates 50.0 milliliters of 0.64 molar hydrofluoric acid, HF, with 2.0 molar sodium hydroxide, NaOH, using a probe to monitor the pH of the solution. The data are plotted, producing the following titration curve. The location of the equivalence point on this titration curve is where that rapid increase in pH occurs, and that would be after 16 milliliters of the titrant is added. So since half of 16 is 8, the location of the half equivalence point would be at a point in the titration when 8 milliliters of the titrant is added. Something special happens at the half equivalence point. At the half equivalence point, the pH is equal to the pKa. So if we estimate the pH of the solution at the half equivalence point, it looks like it's approximately around 3.2 as far as the pH of the solution at the half equivalence point. Remember that pH equals pKa at the half equivalence point. So part A of this question, using the information in the graph, estimate the pKa for hydrofluoric acid. So it's going to be the pH at the half equivalence point, which is approximately 3.2. Now, moving on to part B of this question, it says, 3 different particulate representations are shown below. Cations and water molecules are not shown. So we have HF and F- in the particle diagram. Part 1 of part B says, circle the diagram that shows the most accurate representation of the major species present in a representative sample of the reaction mixture at the point in the titration when 12 milliliters of the titrant, 2.0 molar sodium hydroxide, has been added. So is 12 milliliters before or after the half equivalence point? That's what we should be considering. So if the half equivalence point is at 8 milliliters of titrant added, then 12 milliliters will be after the half equivalence point. So at the half equivalence point, pH equals pKa, and the concentration of F- or the fluoride ion is equal to the concentration of the weak acid, HF, hydrofluoric acid. But when 12 milliliters of the titrant has been added in this titration, this occurs past the half equivalence point. So when you're past the half equivalence point, then the pH is greater than the pKa in this titration, and the concentration of the conjugate base, or F-, is greater than the concentration of the weak acid, HF. And this is a review of something I had mentioned earlier. This is from topic 8.7, pH and pKa. So again, when the solution pH happens to be less than the pKa of the weak acid, then the acid form would have a higher concentration. But on the other hand, in this particular example, if the pH of the solution is greater than the pKa of the weak acid, then the base form has a higher concentration. So we already know, based on the fact that pH is greater than pKa, there should be more F- than HF in our particle diagram. So we're looking for a particle diagram in which there are more F- ions than HF molecules. And that would be the diagram on the far right. So because pH is greater than pKa at this particular point in the titration, then there should be a higher concentration of F- as compared to HF. So we've now answered part 1. We've circled the diagram that shows the most accurate representation of the major species present in a representative sample of the reaction mixture at the point in the titration when 12 milliliters of the titrant has been added. Part 2 is a justify your choice by comparing the pH of the reaction mixture at that particular point in the titration with the pKa of HF. So as I said earlier, we are at a point where it's past the half equivalence point, the pH is greater than the pKa, and that's why the concentration of F-, the conjugate base, is greater than the concentration of HF, the weak acid. All right, well, that is the answer to part B of this question. Now let's take a look at part C. In part C, it says, at the equivalence point of the titration, the pH of the reaction mixture is between 8 and 9. Circle all of the substances listed below that are present in the reaction mixture at a concentration greater than 0.10 molar when the equivalence point is reached. So in this titration, we start with a solution of hydrofluoric acid, or HF, and then throughout the titration we are adding sodium hydroxide, NaOH. So the molecular equation for the acid-base reaction that occurs in this titration experiment is written as follows. HF, or hydrofluoric acid, is reacting with NaOH, or sodium hydroxide, to produce sodium fluoride and water. So at the equivalence point, there should be a large concentration of sodium ions and fluoride ions in solution. And if you're wondering about the concentration of OH-, the pH of the solution is somewhere between 8 and 9. So for example, suppose the pH of the solution is 9. Then the pOH would be 14 minus that value. So 14 minus 9 is 5. And if the pOH is 5, that would place the concentration of hydroxide at a value of 10 to the minus 5. So the instructions said to circle all of the substances listed below that are present in the reaction mixture at a concentration greater than 0.10 molar. So the predominant species that are present in the solution at the equivalence point would just be sodium ions and fluoride ions. All right, now let's move on to part D involving a net ionic equation. So part D says the following: write the net ionic equation for the acid-base reaction that takes place between one of these substances that you circled in part C and water. This reaction should provide evidence to support why the pH of the reaction mixture is greater than 7 at the equivalence point. So is it sodium plus or Na plus, or is it fluoride minus, F minus? Which one of those ions is going to behave as a base at the equivalence point? Well, sodium ions are not going to do anything to affect the pH of the solution at all. Na plus is merely a spectator ion and not contributing to the pH. But since HF is a weak acid, that means that the fluoride ion, F minus, would behave as a weak base. So in solution at the equivalence point, it's going to be the F minus ion reacting with water to produce HF along with the hydroxide ion. So that reaction showing that the fluoride ion is able to behave as a weak base, and therefore that would explain why the pH of the reaction mixture is greater than 7 at the equivalence point. All right, let's take a look at the next part of this question, which is part E. Part E says the following. It says, the student performs a second trial of the titration experiment, this time titrating 50.0 milliliters of 0.64 molar hydrofluoric acid with a solution of 1.0 molar sodium hydroxide as the titrant. Sketch the curve that would result from the titration in trial 2 on the following graph, which already shows the original curve from the titration in trial 1. So the only change that is being made from trial 1 to trial 2 is the concentration of the sodium hydroxide is changing from 2 molar to 1 molar. We're not changing anything about the volume or the concentration of the hydrofluoric acid. We're simply reducing the concentration of the titrant, the sodium hydroxide, from 2 molar to 1 molar. Let's go ahead and process the number of moles of hydrofluoric acid that is being used in each of these trials. So remember that volume times molarity equals moles. So in trial 1 as well as in trial 2, it's 50 milliliters or 0.050 liters of hydrofluoric acid, and the concentration is 0.64 moles per liter. So if I do volume times molarity to get moles, that would be 0.050 liters times 0.64 moles per liter. And that gives me a value of 0.032 moles of hydrofluoric acid. Based on the 1-to-1 mole ratio between hydrofluoric acid and sodium hydroxide, then I need 0.032 moles of sodium hydroxide to reach the equivalence point. So in trial 1, it was a 2 molar solution of sodium hydroxide, and it required 16 milliliters of the titrant to reach the equivalence point. So take a look at this math. That would be 0.016 liters times 2 moles per liter, and you can see that I get 0.032 moles of sodium hydroxide. So in trial 1, 16 milliliters of the titrant was needed to reach the equivalence point. So in trial 2, if I reduce the concentration of sodium hydroxide from 2 molar to 1 molar, then I will need twice as much volume of the titrant to reach the equivalence point. So to show you that math, it would be 0.032 liters or 32 milliliters times 1 mole per liter for the concentration, and that would give me that same amount of moles of sodium hydroxide. So what we're doing in trial 2 is that the titration curve will be shifted over to the right so that the volume of the titrant that is required to reach the equivalence point is going to be 32 milliliters. So before I sketch the titration curve for trial 2 on this graph, I'd like to examine certain features of the titration curve from trial 1. And the 3 points that I'd like to examine are the initial pH, the pH at the half equivalence point, and the pH at the equivalence point. So in trial 1, looking at that titration curve for trial 1, the initial pH is approximately 1.7. The pH at the half equivalence point, which occurs after 8 milliliters of the titrant has been added, that pH is approximately 3.2 at the half equivalence point. And then at the equivalence point, which occurs after 16 milliliters of the titrant has been added, that pH is approximately 8.5. So now let's do a compare and contrast between trial 1 and trial 2. So with trial 2, the initial pH should be the same as it is in trial 1. And the reason why the initial pH should be the same is because we're not changing the concentration of hydrofluoric acid. So that initial pH should still be about 1.7. As far as the location of the equivalence point, because we have shifted toward the right, the location of the equivalence point, now it's going to be after 32 milliliters of the titrant has been added in trial 2, then there should be a pH of approximately 8.5 on this curve, but it would be shifted over from 16 milliliters to 32 milliliters. Now, since half of 32 is 16, then that means that in trial 2, the location of the half equivalence point, which would be a pH of approximately 3.2, that would occur at the 16 milliliter mark on the x-axis. So these 3 points, the initial pH, the pH at the half equivalence point, and the pH at the equivalence point that are marked in red on this slide, these are my guidelines for how I can sketch the curve, the titration curve for trial 2 on this graph. So what I'm going to do is follow the general shape of the titration curve. So it's going to be a relatively flat pH in the region of the half equivalence point, because that's the buffer zone or the buffer region. Then there should be a sharp increase in pH that occurs at 32 milliliters that matches the initial shape of the titration curve for trial 1. And then after the equivalence point has been reached, then the pH will level off to a similar value, so around 13 or so past the equivalence point. So these 3 points that I'm highlighting on the slide, indicating the important features of the titration curve for trial 2, are the initial pH should be the same as it was in trial 1, about 1.7. The pH at the half equivalence point is approximately 3.2, and that would occur at 16 milliliters of NaOH added. And then the pH at the equivalence point would be approximately 8.5, and that would be occurring on the x-axis after 32 milliliters of the titrant is added. So those are the features I'd be looking for in this curve. All right, now let's move on to question 7. Question 7 says the following. Information about 3 different weak acids is shown in the table above. Use this information to answer the following questions. So in the table, we are given the chemical formulas of 3 different weak acids, and they are, from left to right, HNO2, which is known as nitrous acid, HOCl, which is known as hypochlorous acid, and NH4+, which is known as the ammonium ion. They all behave as weak acids, and we are given the Ka value for each one of these substances. In part A, it says a student prepared a buffer solution by combining 500.0 milliliters of 2.0 molar nitrous acid and 500.0 milliliters of 1.0 molar potassium hydroxide. calculate the pH of the buffer solution prepared by the student. Now, when you are given volume and molarity, a good strategy is to go ahead and calculate the number of moles of each substance. So we are given volume in milliliters. We're going to divide by 1,000 to go from milliliters to liters. So 500 divided by 1,000 would be half a liter. So for the nitrous acid, HNO2, we have half a liter, so 0.5 liters, of a 2 molar solution. That would be 2 moles per liter. 0.5 liters times 2 moles per liter. That tells us that we have 1 mole of nitrous acid. And then we'll do a similar calculation for the potassium hydroxide, the KOH. The number of moles of potassium hydroxide would be half a liter, so 500 divided by 1,000 is 0.5. 0.5 liters times 1 mole per liter. So we have 0.5 moles of potassium hydroxide. And since potassium hydroxide is a strong base, that means that we have 0.5 moles of the hydroxide ion. So what happens when a weak acid reacts with a strong base? What you get when a weak acid reacts with a strong base is you get water, and you also get the conjugate base of the weak acid. So HNO2, the weak acid, is reacting with OH minus hydroxide from the strong base to produce NO2 minus, which is the conjugate base of nitrous acid, and water. Now let's focus on the quantities. We have 1 mole of nitrous acid, and we have 0.5 moles of hydroxide. On this next slide, this is from an earlier video where I was talking about buffers and different ways of combining solutions together to prepare a buffer. Take a look at the highlighted row of this table. So one way to prepare a buffer is to combine a weak acid with a strong base in such a way that you reach the half equivalence point. In other words, the number of moles of the hydroxide ion, if it's half as much as the number of moles of the weak acid, then you will produce a buffer solution in which you have equal amounts of the weak acid and its conjugate base. That's exactly what we're doing in this buffer solution. So when these two solutions are combined to make a buffer solution, it's going to produce an equimolar mixture of the nitrous acid, HNO2, and its conjugate base, NO2 minus. So when you have an equimolar mixture of the weak acid and its conjugate base, the pH of that solution is equal to the pKa. So now we can answer this question. Calculate the pH of the buffer solution prepared by the student. The answer is it's going to be the pKa for nitrous acid. And that is the negative log of the Ka. So the negative log of 4.0 times 10 to the negative 4 gives us a pH of 3.40. And that number is the pKa for nitrous acid. So we combined 1 mole of nitrous acid with 0.5 moles of hydroxide, producing an equimolar mixture of HNO2 and NO2 minus. pH equals pKa, which is the negative log of the Ka, 3.40. Now, on to the next part of Part A. It's a particle diagram. So the particulate diagram shown below only displays HNO2 particles. And there are 6 HNO2 particles that are featured in the diagram. It says this diagram is incomplete. Draw in the correct number of NO2 minus ions in the box below so that the diagram shows a representative sample of the buffer solution prepared by the student. So we know that this buffer solution contains an equimolar mixture of HNO2 and NO2 minus. If there are 6 HNO2 particles that are featured in this diagram, then we should draw in 6 NO2 minus ions. 1, 2, 3, 4, 5, 6. So the answer to this part, as far as completing the particulate diagram, is that 6 NO2 minus ions, represented by the white circles, should be added to complete this diagram. Now let's take a look at Part B of this question. In Part B, it says circle one of the following pairs of solutions which, when combined, will result in a buffer solution with a pH that is greater than the pKa of HOCl. So HOCl is a weak acid, that is hypochlorous acid, and in all three of these possible combinations of solutions, we're combining 0.10 molar hypochlorous acid, HOCl, with another solution that is also 0.10 molar, but that's NaOCl, or sodium hypochlorite. So we're combining the weak acid, HOCl, with its conjugate base, OCl-. And since each solution has the same concentration, 0.10 molar, it must be about the different volumes that are being combined. So I'll start with the middle combination. We have 100 milliliters of 0.10 molar HOCl, and we have 100 milliliters of 0.10 molar NaOCl-. So in that middle combination, you would get an equimolar amount of both the weak acid, HOCl, and its conjugate base, OCl-. That would result in a buffer solution in which the pH is equal to the pKa. So we can rule out that middle combination of solutions as the possible answer. So the correct answer to part B is either the first combination or the third combination. Let's take a closer look at those two results. We have 50 milliliters of 0.10 molar HOCl, but then we have 100 milliliters, so twice as much, of the 0.10 molar sodium hypochlorite, or NaOCl. So in that first combination, there is more OCl- than HOCl. And then the third combination, it's the opposite. It's the other way around. We have 100 milliliters of 0.10 molar HOCl and 50 milliliters of 0.10 molar NaOCl. So in that third combination, there is more of the weak acid, HOCl, than there is of the conjugate base, OCl-. So we know that the correct answer to part B is either the first combination or the third combination, because the pH is not the same as the pKa. What we're looking for is a solution in which the pH is greater than the pKa of HOCl. So what guides us in making the correct choice in part B is this information from topic 8.7, pH and pKa. If our buffer solution has a pH that is less than the pKa of the weak acid, then the acid form has a higher concentration than the base form. But on the other hand, if the buffer solution has a pH that is greater than the pKa of the weak acid, then the base form has a higher concentration than the acid form. That's the kind of buffer that we're looking for in this question. pH greater than pKa, there should be more OCl-, which is the conjugate base, and there should be less HOCl, which is the weak acid. So we're looking for a solution in which there is more OCl- than HOCl. So that's why the correct answer to part B is this first combination. Because the pH of the buffer solution is greater than the pKa, then there should be more of the conjugate base than the weak acid. And now, moving on from part B to part C, we actually need to do the calculation. So in part C, it says calculate the pH of the buffer solution formed from the combination of solutions that you circled in part B. So to answer part C of this question, we need to apply the Henderson-Hasselbalch equation. So take a look on this slide. This is from topic 8.9. The Henderson-Hasselbalch equation involves pH equals pKa plus the log of the ratio of A minus over HA. In other words, the log of the ratio of the conjugate base over the conjugate acid. So in this example, it's going to be the log of the ratio of OCl minus over HOCl. So the solution that we circled, it's going to have a ratio of OCl minus to HOCl that is going to be 2 to 1, because the number of moles of OCl minus is twice as much as the number of moles of HOCl. There's 100 milliliters of a 0.1 molar solution of NaOCl, and there's only 50 milliliters of a 0.10 molar solution of HOCl. So the number of moles of OCl minus is twice as much as the number of moles of HOCl. So pH equals pKa plus the log of the ratio of A minus to HA. Now, to get the pKa, we have to take the negative log of the Ka. So that's given to us in the table. The negative log of 2.9 times 10 to the negative 8 will give us the pKa. And as far as the ratio, it should be 2 to 1. So it's going to be 7.54, which is the negative log of 2.9 times 10 to the negative 8, plus the log of 2. That's going to give us our final answer if we do this calculation. 7.54 plus the log of 2. That gives us 7.54 plus 0.30. And our final answer, the pH, is 7.84. Again, this is consistent with our prediction. Since 7.54 is the pKa of hypochlorous acid, the answer in part C is 7.84. So yes, the pH of this solution is in fact greater than the pKa for hypochlorous acid. Now, before we take a look at part D of this question, let's process the information that was given in the table about two different buffer solutions that were prepared. So it says two different buffer solutions were prepared that each contain an equimolar mixture of NH3, which is ammonia, that's a weak base, and NH4+, which is ammonium, that's a weak acid. An experiment was performed in which a small amount of sodium hydroxide, that's a strong base, was added to 1 liter of each buffer solution. The pH of each solution was measured before and after the addition of the sodium hydroxide. Data from the experiment are shown in the table below. So we have buffer solution number 1, and the concentration of each component in buffer solution number 1 is 2.0 molar. It's 2.0 molar ammonia, NH3, and 2.0 molar ammonium, NH4+. That is a conjugate acid base pair where ammonia is the weak base and ammonium is its conjugate acid. For buffer solution number 2, it's the same components, but the concentration of each component is 1/10 as much compared to buffer solution number 1. So the concentration of ammonia is 0.20 molar. And the concentration of ammonium is 0.20 molar. Now that difference in concentration is related to a concept known as buffer capacity. And we're going to see that coming up in this question. All right, the volume of each buffer solution is the same. It's 1 liter for both. The initial pH of the buffer solution is the same. It's 9.25. And if you're curious about where did that 9.25 come from, well, if you go back and look at the table, we have the Ka for the ammonium, NH4+, and it's 5.6 times 10 to the negative 10. So when you have a solution in which the concentration of the weak acid is the same as the concentration of its conjugate base, then pH equals pKa for that solution. So if you take the negative log of 5.6 times 10 to the negative 10, you will get the pKa for this weak acid, for ammonium, and that is why the pH of each buffer solution is 9.25, because the pH equals the pKa when the concentration of the weak acid and its conjugate base are equal. Again, we have a difference in buffer capacity, which we will see coming up. That's going to be part of the question we have to answer. The amount of sodium hydroxide added to each buffer solution is 0.10 mole, and the final pH of the buffer solution after sodium hydroxide is added, we are told for buffer solution number 1, it was 9.25 before the sodium hydroxide was added, and it increased to a value of 9.30. So that's a difference of 0.05. So the magnitude of change in pH for buffer solution number 1 was 0.05. Now you'll see question marks in the other column because we have to make a prediction about the magnitude of change in pH for buffer solution number 2. All right, now let's go ahead and take a look at part D. Part D talks about what happens when sodium hydroxide, which is a strong base, is added to these buffer solutions. Write the net ionic equation for the acid-base reaction that occurs when sodium hydroxide is added to these buffer solutions. So sodium hydroxide contains OH minus. OH minus is for a strong base. That's going to be the major reacting species, OH minus. Now, will OH minus react with a weak base or a weak acid? NH4 plus is the weak acid. NH3 is a weak base. So a strong base does not react with a weak base, but instead a strong base will react with a weak acid. So on the left, in your net ionic equation, it's going to be OH minus plus NH4 plus. So the strong base reacting with the weak acid. And then on the right, you're going to produce water and ammonia, which is the conjugate base of ammonium. So OH minus, the strong base, reacts with NH4 plus, the weak acid, to produce the conjugate base, NH3, and water. Now, let's take a look at part E of this question. So part E of this question deals with that concept of buffer capacity. It says an equal amount of sodium hydroxide, 0.10 mole, was added to each buffer solution in this experiment. Do you predict that the magnitude of change in pH for buffer solution number 2 will be less than, equal to, or greater than 0.05? Justify your answer by comparing the buffer capacity of solutions number 1 and number 2. Now, what I'm going to show you on the next slide is actually something I had presented in a previous video. So in a previous video, when I was talking about topic 8.10, which is buffer capacity, I had given an example of 2 different buffers that also happen to be labeled number 1 and number 2. So at the bottom of this slide, you can see I've highlighted one of the essential knowledge statements from topic 8.10, buffer capacity. It says, increasing the concentration of the buffer components while keeping the ratio of these concentrations constant keeps the pH of the buffer the same, but increases the capacity of the buffer to neutralize added acid or base. So one hallmark of a buffer is that it is able to prevent the pH from changing dramatically. So take a look in the middle part of the slide for the data for buffer number 1 and buffer number 2. Again, this is from a different problem from a previous video. So you can see that buffer number 1, its concentration of buffer components is higher. It's 1 molar, whereas buffer number 2, its concentration of buffer components is smaller. It's 0.05 molar. So what happened in this problem from a previous video is that a small amount of a strong acid was added to these 2 buffer solutions. Notice that the initial pH is 4.74 for both, but for buffer number 1, the one that had the greater buffer capacity, its pH only decreased by 0.04 pH units. And buffer number 2, which had the smaller buffer capacity, it experienced a much greater change in pH. It went from 4.74 all the way down to 3.47. So the message from this slide is that the higher the buffer capacity is, the smaller the magnitude of change in pH will be when a certain amount of either a strong acid or a strong base is added to the buffer. And then you could say that the other way around. The smaller the buffer capacity is, the greater the magnitude of change in pH will be when a small amount of either a strong acid or base is added to that. So now let's go back to the current question. Again, this was from part E we're going to take a look at. So we have buffer number 1, higher buffer capacity or greater buffer capacity, and buffer number 2, smaller buffer capacity. So here's our prediction. What would happen when 0.10 mole of sodium hydroxide is added to buffer solution number 2? Because it has a smaller buffer capacity, it's not going to be as able to absorb the added sodium hydroxide, and the pH should change more dramatically. So here's our prediction, that the solution with the smaller buffer capacity should experience a greater magnitude of change in pH when either a strong base or a strong acid is added to the buffer. So that's going to be how we answer part E of this question. So here's my answer to part E. The magnitude of change in pH for buffer solution number 2, I predict will be greater than 0.05. And my justification is because buffer solution number 2 has a smaller buffer capacity than buffer solution number 1. Okay, now let's take a look at question 8. Question 8 says the following. The dissolution of solid calcium hydroxide in water is represented by the equation above. 3 different beakers are shown below that contain 100 milliliters of a different substance. In a certain experiment, excess solid calcium hydroxide is added to each one of these beakers. The solution in each beaker is stirred until no more solid dissolves. So in beaker number 1, we have 100 milliliters of a 0.50 molar solution of nitric acid, HNO3. In beaker number 2, we have 100 milliliters of a 0.50 molar solution of sodium hydroxide, NaOH. And in beaker number 3, we have 100 milliliters of distilled water. Now let's take a look at part A of question 8. Part A says the following. In which of the following beakers, so we have to choose between beaker number 1 and beaker number 2, do you predict that the molar solubility of calcium hydroxide will be less than the molar solubility of calcium hydroxide in distilled water? So this question, question 8, falls under topic 8.11, which is pH and solubility. So the essential knowledge statement says the solubility of a salt is pH sensitive when one of the constituent ions is a weak acid, a weak base, or the hydroxide ion. And these effects can be understood qualitatively using Le Chatelier's principle. So we do have a substance that contains the hydroxide ion, that's calcium hydroxide, and it will be affected by either the presence of a strong acid, such as nitric acid in beaker number 1, but it can also be affected by a strong base, such as sodium hydroxide in beaker number 2. So what does less in terms of the solubility mean with respect to the direction in which the equilibrium system for the dissolution of calcium hydroxide will shift? And so if it's less soluble, that would imply a shift in the equilibrium system toward the solid calcium hydroxide away from the aqueous calcium and hydroxide ions. So by putting that arrow on the slide, that gives me some context about what I'm looking for. I'm looking for less soluble, so a shift from right to left or from products to reactants for the dissolution of calcium hydroxide. Now, I'm going to make my choice in part A and then immediately go into the justification in part B. So my choice is beaker number 2, the sodium hydroxide solution. Now, let me go ahead and justify my choice, and I have 3 little bullets to consider in part B. So justify your choice in part A in terms of the following details. The first one says, describe how the value of the concentration of hydroxide is affected by the substance in the beaker that you selected. Well, clearly sodium hydroxide contains both sodium ions and hydroxide ions, but I am focusing my attention on the hydroxide ions. So the value of the concentration of hydroxide increases because of the presence of the hydroxide ions in sodium hydroxide. Next, include a comparison of Q versus K, so QSP versus KSP. Considering that hydroxide ions are present on the right side of that equation at the top of the slide, you're increasing the concentration of hydroxide ions. That will cause Q to become greater than K, or QSP becomes greater than KSP. And now finally, indicate the direction, that is, from reactants to products or from products to reactants, in which the equilibrium system for the dissolution of calcium hydroxide will shift as a result of the substance in the beaker that you selected. So Q being greater than KSP will cause the following. The equilibrium system for the dissolution of calcium hydroxide will experience a net conversion from right to left, or from products to reactants. So this explains why calcium hydroxide is less soluble in the beaker that contains hydroxide ions as compared to distilled water. This also goes back to something from Unit 7 about the common ion effect, that the presence of that common ion, the hydroxide ion, does make calcium hydroxide less soluble in a solution that already contains that common ion. Now, as we move on to parts C and D of this question, I'm going to flip it around the other way. So instead of less soluble, this is what it says in part C. In which of the following beakers do you predict that the molar solubility of calcium hydroxide will be greater than the molar solubility of calcium hydroxide in distilled water? Well, you can already tell what we're going to choose here because it's not going to be sodium hydroxide. So by default, I'm going to be selecting beaker number 1. But what I'm looking for is a shift in the equilibrium system for the dissolution of calcium hydroxide from left to right, or from reactants to products. So I'm trying to favor the dissolution, favoring the formation of those aqueous ions. So pretty much everything I'm going to say in part D as my justification will be the opposite of what I had mentioned in part B of this question. So here we go. Justify your choice in part C in terms of the following details. First, describe how the value of the concentration of the hydroxide ion is affected by the substance in the beaker that you selected. So what will a strong acid, such as nitric acid, do to affect the concentration of the hydroxide ion? Well, the value of the concentration of the hydroxide ion decreases because the H+ ions from the solution of that strong acid, nitric acid, react with the hydroxide ions. And so the acid-base reaction is H plus OH minus to make H2O. And so when hydroxide ions are consumed as they react with the strong acid, then their concentration will actually decrease. Next, include a comparison of Q versus K. So how will QSP compare with KSP? If you're decreasing the concentration of the hydroxide ions, then the value of QSP becomes less than KSP. And then finally, indicate the direction in which the equilibrium system for the dissolution of calcium hydroxide will shift as a result of the substance in the beaker that you selected. So because the concentration of the hydroxide ions are decreasing, because Q becomes less than K, the equilibrium system for the dissolution of calcium hydroxide will experience a net conversion from left to right, or from reactants to products. And so this explains why calcium hydroxide is more soluble in the beaker that contains that strong acid that contains H+ ions as compared to distilled water. So again, question 8 was an example of topic 8.11, pH and solubility. All right, well, question 8 was the last question in the Unit 8 summative assessment practice. I hope that you found all of these answers and explanations helpful. So good luck studying for your Unit 8 summative assessment, and thanks for watching.